So our next speaker is Sandeep Chatterjee, and Sandeep is from IISER Barampur. Of course, Sandeep do a lot of work in many different areas. So it is indeed nice to have him here and listen from him. So Sandeep, please.
Okay, thank you, Santosh. Thank you to all the organizers for this nice invitation, nice school going on. So let me start. I think some of these things have been discussed, so that makes my job easy. So, I mean, if you have questions, maybe we can discuss more than simply reading off from the slides. So what I have done, using heavy probes and trying to point out a few applications, right, where we can use heavy probes to learn about the fireball that we produce particularly in heavy ion collisions. So the topics that I have chosen, basically because those are the things that I have worked on with heavy probes, is mainly from the initial conditions, a few aspects, which also Bedang in the previous talk mentioned about. And then eventually I'll try to introduce a new set of novel observables, and I'll try to tell how that can make our life much easier, possibly. So let's go on. So when I say initial condition, of course, a lot of things can come to mind, pre-equilibrium dynamics, this and that, but that is why I try to really now specify what exactly I mean for this talk as initial condition. So what I would refer to for this talk is the initial geometry that we produce in heavy ion collision, or to be more specific, the initial geometry that will go into your hydro evolution code, for example, right? The thermalized medium that produces, which then starts evolving hydrodynamically. So what is the initial condition for the hydro equations? What is the geometry of the fireball in the coordinate space that you start with to run your hydro equation? So that's the kind of initial geometry, which may not be the geometry at the time of collision, right? You understand, between collision and the starting time for hydro, there can be many complicated things going on, which right now is like a black box. But then we are asking, what is this initial condition from where I can start, I should start my hydro, right? So that is my initial geometry. And then, of course, by now you have already heard, there are these electromagnetic fields loitering around, and they are quite large in the initial, particularly in the initial times. So we'll try to see how the heavy probes are good probes of this initial geometry and the initial electromagnetic fields. So that's the first part. So when we talk of initial geometry, this is the very famous, quite oftenly quoted plot. So let me start with that. And maybe, so this is an example of a near central collision, by which we mean that these two nuclei, which are colliding along the z-axis. So the usual convention is the z-axis is your beam axis, right? And you have two nucleus which are separate, and their centers are separated by some impact parameter b. So the impact parameter axis is usually the x-axis, right? And then the reaction plane, that is why this xz plane is your reaction plane, the plane formed by the impact parameter axis and the beam axis, right? So these are the starting definitions, conventions, so to speak. And so in this reaction plane, if the b, the impact parameter, is small, then what we call is a central collision, right? B0 or B small compared to the radius of the nucleus, right? The radius is a scale, and now the impact parameter, how small, or is it comparable to the radius, or is it larger than radius, right? Accordingly, it's a central collision, mid-central collision, or even a peripheral collision. So the right diagram is like a near central collision, whereas this would be the situation when the impact parameter is a little larger, so that's like a peripheral collision. So if you now, so that's the picture. Now the usual picture, another way you see the same picture is if you take a transverse slice of this thing, right? At a z constant. Let's say at z equals to 0, we do a slice, so then we get these transverse plane diagrams, right? In the xy plane. So then, of course, what we say is that the overlap zone, right, here or here is like an ellipse, and hence you get this cos 2 phi modulation in the momentum space, right? Because the spatial, there is a spatial anisotropy in the coordinate space, right, which is less in the central collision, and then as you go to mid-central and peripheral, this spatial anisotropy enhances. So the corresponding, when the fireball evolves hydrodynamically, this coordinate space spatial anisotropy, right, transfers into the momentum space, momentum anisotropy, right, which is this azimuthal momentum space anisotropy, and usually a cosine 2 phi, if you convolute that with, which we call as the V2, so that picks up this signature, right? And then, of course, from this diagram, it is clear that this would increase as your centrality, as you go from more central collision towards mid-central or peripheral. So that's a quite common picture. This is called the elliptic flow. And then there is the other kind of flow, which was also mentioned in the previous talk, like the directed flow. So if you have to think about the directed flow, then instead of taking this transverse slice, right, it is recommended that you think of the collision from another point of view. So here the x-axis is like the z-axis. Of course, here you see a different alphabet, which is the eta, which we call as the pseudo rapidity. So this is a space-time rapidity, but I mean, right now you may think of it like z coordinate, okay? Eta 0 means z0. And then as z is becoming positive means this eta is positive, or as z is negative, the eta is negative. But often in our kind of kinematics, we choose to work with, instead of z, this space-time rapidity eta. So if you look at the collision from this perspective of the impact parameter direction and the z-axis, right? So this is in the reaction plane I am now projecting. Then what you see one nucleus which is going this way, the red colored one which is going right side, and the blue colored one which is going left side. So now you concentrate on some x equals to constant slice here, right? These portions are of course spectator because they don't see anyone coming from this side, so they don't participate. So these we call as spectator, these we call as spectator, and only this portion is the overlap zone which participates in the collision. So that ellipse now is basically here, right? But we are now not looking at it from the xy plane, so it doesn't look like an ellipse. We are looking at it from in the reaction plane. But that is to develop the idea of directed flow, right? So now if you see at a constant x slice, right, you should notice the following. When I am at a positive x, you see at a given x value, there are more participants from the red nucleus which is moving along the positive z direction or positive eta direction compared to participants from the blue nucleus which are moving along the negative z direction or negative eta direction, right? Just because this thickness is larger than this one. Simple geometry. And similarly, symmetrically, if you go towards minus x direction, you just see the opposite thing. More of the blue participants moving to the left compared to the red participants moving to the right, right? So there is this, this is what we would call as a forward-backward asymmetry. Although it's the same nuclei which are colliding, but as soon as you go off central, at constant x slices, there are these forward-backward asymmetry that is there in your geometry. This is very important because this gives rise to consequences, observational consequences. So this idea of the initial geometry plus the following measurement. So what I am showing here is D-gold collision, okay, at 200 GeV measured by Phobos experiment, which is one of the 4 experimental collaborations at the relativistic heavy ion collider. So Phobos has a large rapidity coverage, and what you see here is dn charge d eta, charged particle multiplicity, okay, in the y-axis, and in the x-axis it is pseudo rapidity eta, right? Like here it was space-time rapidity. This is rapidity constructed out of momentum space. So if you find it difficult, I don't know whether this eta was introduced in this school, you can just think of it like your pz, z component of the momentum. It's quite similar, just to understand. So here actually you see this, for example, the central collision, right? This is 0 to 20%. The convention is 0 to 20% is like the most central. That means the impact parameter is smallest. And then you see we go towards mid central and then peripheral. So the striking feature is in the central collision to mid central collision, this multiplicity distribution has a asymmetry in this rapidity. I hope you see that. There are less particles being produced in the forward hemisphere plus pz side compared to negative pz, where in the negative pz we are producing more particles. And then as you go towards very peripheral, you see this asymmetry is gone, right? Now here the gold going direction, right, because this is a deuteron gold collision. So anyway the collision system itself is asymmetric, right? So the gold going direction is actually minus z. So the gold is actually moving from right to left. So in a very central collision, it's like one of these slice, right? Because the deuteron is just 2 participants, whereas the gold will have a few depending on where is the impact parameter. So each of these slice is like a deuteron gold, in some sense you can think of it, right? So what this is saying is a given participant prefers to produce final state particles along the direction of its initial motion, right? So here what we see, there is asymmetry in the number of participants moving in the forward or backward hemisphere, and this also happens in d gold. And from here, if I have to explain this, I have to put in the fact that these participants deposit entropy or deposit energy in the firewall asymmetrically. The red ones, they will deposit more entropy in the forward hemisphere. The blue ones, because it is moving in the negative z, it is going to deposit more in the negative z direction, right? Because that is clear from this d gold. In the d gold, in the gold going direction, more multiplicity we see, right? And that's because the gold participants, they deposit more multiplicity in the direction in which they move. If they had all deposited in a forward backward symmetric way, then even though d gold is an asymmetric system, you would have still observed a flat multiplicity distribution in the final state, right? Because it doesn't matter even if there is forward backward asymmetry in the initial state, if they are going to deposit energy or entropy in a forward backward symmetric way, then the firewall produced is a forward backward symmetric. Then the multiplicity that will come from that will also be forward backward symmetric. So this asymmetry is because of twofold reason. The fact that it's an asymmetric system and this crucial thing, because this you cannot derive really from a first principle. It is very non-perturbative physics. This you have to put in by hand, and the only way to achieve it is that the participant is asymmetrically depositing entropy in the initial state. It is depositing more in its direction of motion. Okay, so this is something we will forward backward asymmetric deposition by a participant source. This is an ansatz. We have to start with this. Then we explain this, and when we put this in this thing, right, then what you get is the following. Because these guys are depositing more in this direction and these guys are depositing more in the backward direction, the firewall that is created, right, is kind of this one, right? And this is what was called, like in the previous talk, as a tilted firewall. This firewall is not parallel to the beam axis, right? Depending on whether it is positive x or it is negative x, right? This firewall has more entropy deposition, right, in the forward hemisphere or in the backward hemisphere, and that's because of this forward-backward asymmetry that is there in each slice of the initial geometry. So this is very crucial. If you get this, this is like a one-slide summary of a major part of what I'm going to discuss, right? So this is the geometric origin of this tilted firewall, and what you can then see that if you have that phi, the V2, for that V2, we had to do a cos 2 phi average because it was an ellipse. However, here you see if you have a cosine phi average, this is going to pick up non-zero. And then this is called the directed flow, right? So this is the origin of rapidity odd directed flow. Why this is rapidity odd? Because you see if in the positive z, this is along plus x, whereas if you go to minus z or minus rapidity, this is in the minus x, right? So if you flip rapidity, the V1 actually will flip sign, and that is what we see in experiment, right? This is experiment now, right? Measurement V1 or this rapidity or directed flow with eta or the pseudo rapidity, and this is star experiment, and you see more central collision is this one, the red points 0 to 5% centrality, and then 5 to 40 or more peripheral this. So this is a rapidity odd, right, structure. So to explain that, this Bose-Einstein scale, so they have basically proposed this thing that one gets from this initial geometry, this rapidity odd structure, which can capture this rapidity odd directed flow.
This tau naught is the
starting time. Starting time, yeah,
Right.
yeah, right.
And they use viscous hydro? Or?
Yeah, yeah. Right. So far, yeah. This one, right to left. Right, right. That is why this is skewed to the left. So that was light flavor. This talk is about heavy flavor. So now comes the heavy flavor. Now I hope I have convinced you that the light flavor firewall, right? So that is this blue kind of thing. We are still in this x eta plane, right? And because we have produced this tilted firewall, this one I am now drawing by this blue thing, right? The heavy quarks have a different way of being the production mechanism in a heavy ion collision. They are mainly by forward-backward symmetric processes, hard scatterings. So those are forward-backward symmetric. So that is here. In this cartoon, it's like this red thing. And so you see when this firewall, due to hydrodynamic expansion, okay, this is going to rotate in this clockwise direction. And when it will do so, because the heavy quarks are preferentially on one side of the firewall at positive rapidity, they are going to be pushed on one side asymmetrically, right? And then the opposite thing is happening in the other end. So this is the mechanism due to, sorry. Yeah, so what I'm saying is this thing here, this is now a cartoon diagram where I am representing by this blue thing because it is tilted. But now, how are the heavy flavor? Because you heard in the previous talk, right? The heavy flavor is being produced in the firewall at a very early time. They cannot be thermally produced because their mass is much larger than the firewall medium temperature. Bath cannot produce heavy quarks. If they are there, they are being produced at the very early times, right? Now the question is, where are they being produced? So we often what is thought, they are produced due to hard scatterings, okay? So those hard scatterings are forward-backward symmetry. They are not tilted like this, okay? So then this my red thing is my cartoon for how the heavy quarks are produced. And now, because, so what you see in the positive rapidity, these red things, the heavy quarks, they are preferentially being produced on one side of the fireball. So as due to hydroevolution, this red thing will slowly move clockwise, okay? Because, and then when that will happen, it will drag the heavy quarks preferentially on one side. And here just on the other side, okay? So that is the mechanism which can provide to charm or anti-charm a much larger directed flow than the light flavor itself, right? So in order to, of course, yeah. Sorry? No, or rather it will be large, because this, when it will flow, it will push all the heavy flavor to down, right? So then what it means, we will see that the heavy flavor will get a much larger directed flow than the light flavor. It's almost 10 to 20 times larger, which Vedant already mentioned in the previous talk. So I'm just telling you the mechanism for that. So of course, from this initial condition to really do the calculation via Langevin dynamics, Santosh has already expanded on those in the previous talks. So of course, you need to know how much is this bulk tilted, and also the heavy flavor and the bulk, they are talking to each other via this drag coefficient, right? The drag is the thing which is basically the fireball is going to drag the heavy flavor with itself via this drag coefficient gamma, right, which he was writing yesterday. So we can fix, we do the Langevin evolution, and we try to tune the drag roughly by looking at RA and V2, and then we find some intermediate range in which we can capture all that. So with that, when we do look at the directed flow V1, you see, depending on how much drag we put, we get almost 10 to 20 times larger V1 for the heavy flavor. So here you see the charged particle heavy flavor are these triangles, okay? Whereas all these symbols, these are for heavy flavor. So as you see, they're almost 10 to 20 times larger if you really sit down and do that. And that was what is seen in the experiments, that you see this is the kaon, K plus K minus, which is here, whereas the D0 plus D0 bar. So the heavy flavor here is like I'm looking at open heavy flavor. So the charm along with a U or a U bar, right? So that's a D0 plus D0 bar, and that is this one. So if you look at their slopes, the D0 slope is almost 20 times larger than the kaon slope, which is the light flavor. So that's one of the fantastic things, that the heavy flavor is a much more sensitive probe of this initial collision geometry that we produce in heavy ion collisions, right? And then this tilt that I'm telling you, right, it is also source of the angular momentum, right? Because when you produce this thing, right, so this is moving, so there is angular momentum that is you have deposited. And so that same mechanism hence will also give rise to polarization, spin alignment, those things that were mentioned in the previous talk. And of course, I think Amresh next week is going to speak more on this. Yeah. Exactly. It's another way of depositing the initial angular momentum into the fireball.
So see, this V2, V1, these appears because there was this initial kind of elliptic shape, and then we want to Fourier expand basically. And the second term was giving V2 and first term is V1 like that. So it was actually expansion in Fourier expansion. Now that in this new situation we have this tilted structure, and we also have some sort of a angular momentum involved. Don't you think that rather than Fourier expansion, a expansion in a complete basis of spherical harmonics would be a better basis to expand?
Yeah, definitely. In fact, in my new observables, I'm doing one step further, which is in the radial direction, so that we can set up the Fourier Bessel kind of a decomposition. But for full 3D, like people have now introduced in rapidity some of such kind of basis functions. Yeah. But those V2 is actually in the transverse plane, whereas this directed flow or angular momentum always involves the z axis, because it is about how you break boost invariance. If you don't break boost invariance, then there is no angular momentum or anything, right? Yeah. Okay. So, so that was about the tilt. And next is, of course, going back to this picture, if you move your attention from the participant zone to the spectators, they are doing one thing great. And that is, as they are flying off, right, they have a large current, right, because there are protons there, not only just neutrons, there are charged particles which are protons. So this spectator bunch and this spectator bunch, you can think of like a current carrying wire. So there are these two parallel current carrying wires, and you can do your class 10 or whatever school thing to find out what is the magnetic field at the center of the wire of two infinite pairs. So you, given if you put these distances, which are some Fermi, and this current is huge because this velocity is like close to speed of light, it turns out that this magnetic field is one of the largest even compared to astrophysical objects, right? However, as you can see that it is largest, of course, when it is at close to z equals to 0, but quickly it is receding. So as it will go further away, it will the field values will fall off like 1 by r cube or something like that, right? So they can be very short-lived. So that is the compensating thing, trade-off. Because of the large velocity, the field is large, but again, because of the large velocity, it will quickly recede, and again the field will fall down. So that's the catch-22 situation, and also it makes it more challenging. So you have a large B field, and then if you think that the QCD, there is a medium form, then there should be, because it's a changing magnetic field, right? It's not magnetostatic, but magnetic field is changing. There is an automatic response in the medium with finite conductivity to retain that magnetization, right? So then there will be a suitable electric field or current in suitable direction such as to maintain the magnetic field. So you will have both electric and magnetic fields generated and whatnot, and that makes this whole thing quite complicated to look at, which we do. All these people have tried to put these things together down, and this is the prediction for charged particle or light flavor, right? So if there is a split, there is this directed flow, but there is a split in the directed flow between the positive and negative charged particles due to this electromagnetic field. But what you must look at here are these numbers, right? There are 1, 2, 3, 4, so about 10 to the minus 5 order, right? And now when we do this same thing, Santosh and all of us here, so you see these numbers are almost 1,000 times larger. There is 10 to the power minus 2, whereas previously this was 10 to the power minus 5, right? So again, these heavy probes are fantastic probes, and this again comes because they are produced early, and the electromagnetic field is also strongest at the earliest time. So you really use that advantage that these are early witnesses, and that really helps us to get this large sensitivity. Of course, the data is now very interesting. I told you for the average V1, that means D0 plus D0 bar. So what is D0 and D0 bar? Maybe we can spend a minute there. In the D0, there is charm, whereas in the D0 bar, there is anti-charm. Now that is important from the point of view of electromagnetic field, because the charm and the anti-charm are carrying opposite electric charge, right? So if I just take the average, then that one is insensitive to the electromagnetic field, but it is sensitive to this overall firewall tilt, which I mentioned first, right? And that we managed to capture, and all that is settled. However, if you look at the difference, delta V1, right, that this tilt cannot source it, right? Because the tilt overall firewall will push the charm and anti-charm in the same way, right? The drag will drag the charm and anti-charm in the same way. However, the electromagnetic field will treat them differently because the charm and anti-charm carries opposite charges. So that is the idea here, and so that's why they do delta V1, which is D0 minus D0 bar, and compare it with a light flavor thing like K minus minus K plus. So the triangles you see here are almost consistent with 0, right? Because they are supposed to be 10 to the power minus 3 times smaller than what you will see for heavy flavor. So they are almost here like 0. For star, well, the mean values have something, the large error bars. The theory expects that this slope, delta V1 slope, should be negative. Of course, the kind of conductivity that we have assumed and all, those are very important here. But whatever ballpark numbers we have put in, according to that, this thing is supposed to be negative. You see this one is sitting here. If you ignore this thing seems to suggest, okay, there may be a trend, but of course with large error bars. But at Alice, at LHC, right, this delta V1 here, now the error bars are much smaller, and it seems this slope is in the opposite direction. It has a positive slope, right? So there is some tension here between what the data is showing here versus here. The model, of course, we have done the calculation at star as well as at LHC energy, and if this is the mechanism which I just spoke to you, we don't expect any change of slope between top RIC energy and Alice energy. For us, the slope is still this, as it is here. However, in data, they seem to see something like this. So it is still an open thing. I think right now, as previously in the previous talk it was mentioned, this analysis with more statistics is going on, and possibly we'll see something. But one thing interesting to see here is that this D0 minus D0 bar, this slope is similar to what they see in the light flavor, right? So it could suggest that there is something more than what we have just discussed here.
Question.
Yeah.
So, Sandeep, when we measure any V1, we have seen there is a strong PT dependence. So it's a
negative, and then it goes
yes.
positive. Correct.
So, what do you think that it is possible that because at LSC the spectrum is much harder than RIC, then the shape is different?
Good, you reminded me. I thought to mention, but I forgot. We were just discussing, me and Santosh. You see here in the star, I think it is, here it is not mentioned, but they possibly take PT from 0.8 GeV or something, whereas in the LHC they took it above 3 GeV. So that is why I asked also Vedang that are they going to get a lower PT bin, and he promised. I think he mentioned possibly they are going to get. So yeah, so all those various factors are playing a role possibly. Okay, so now the final thing. How much time do we? Okay. So coming to this novel observables, so this is something that I've been doing with Kaiser and Trubhuvan. Kaiser is, I mean, both of them have just completed their PhDs. So, and the motivation is coming back to the slide that I showed earlier. For example, this drag coefficient you have, there are various microscopic theories or models, but it's not clear exactly what should be the temperature dependence, right? For example, we took, it has a dimension of temperature, so it's there, but then there could be other factors like this. X need not be 0. So we varied X between 0 to 0.5, and we saw it is quite consistent. So the point is the following, as he was saying that could we do a more thorough decomposition. So we measured these hadrons as Px, Py, Pz, and usually what we do is take a mid-rapidity slice. So that means the Pz goes out of question. So what we have is this Px and Py, right? Or in other words, Pt and phi. And usually, hence we talk of Pt dependence and azimuthal dependence, right? So the azimuthal dependence, there have been a lot of discussions in this workshop already. You do a Fourier expansion to extract this azimuthal dependence, right? Cosine phi, cosine 2 phi, directed flow, elliptic flow, and so forth, so on. But what about the Pt dependence, right? Pt dependence we plot like this and we leave it as it is. Just by eye we see something, okay? So we never try to quantify the Pt dependence usually, right? So the point is, are we missing then some important physics here by not quantifying it? So then one could do something. We could try to quantify it. So what it means is you have to invoke suitable basis functions to characterize your radial distribution. Pt is like the radial direction here, right? So what we are doing earlier is characterizing by just this EIM theta. That's the Fourier expansion. But now we also want to characterize the radial R dependence. And in that, we already have a candidate complete set of basis functions, these phi mn's, which are basically Fourier and Bessel functions, right? So we thought, why not use this available Fourier Bessel function? And this is the interpretations of the this radial basis function. If you look at, so now your expansion has two coefficients, right? One for the angular part, and the other is basically characterizing the transverse or the radial part. So if you take a small value here, right, 1, so that is this line, right? Whereas if you take a larger value, this 5, you see that is this one. So that means it is characterizing in terms of the how uniform it is in radial direction or how non-uniform. Lower values of this coefficient means it is quite uniform, right? And a higher value means it is there is a short range PT-PT correlation, right? So if you expand in this basis, right, you are going to separate out physics of large PT-PT correlation and short PT-PT correlation in some sense, right? So we then try to take these drag coefficients, right, of this form, and we vary this x, right, from 0, 1, 2, and so it's basically we take these different drags and we tune this coefficient so as to get the same V2PT almost, right? The idea is we take different temperature dependent drag coefficient and we tune such that the V2PT is almost similar. So if I just stop here, then I'm ignorant about this different temperature dependence of the drag. They are all giving me similar. And then I want to see if I do this Fourier Bessel, whether I can learn more, whether I can extract the fact that these have different drag, right? So we do this, we expand this V2 in terms of these PT coefficients. That means in these different n harmonics, right? And we see really these coefficients to separate out, right? This blue and orange, which are clubbed together here, right? They are just proportional to T. Whereas this one is proportional to T square and this is proportional to T cube. So indeed, it seems like when you do this further decomposition, a finer resolution, right? Then you manage to find these observables which are actually sensitive to which drag you had put in, which V2 was not sensitive to. So it kind of takes us to the next step. And you could do further, you could look in terms of PT, Y mean PT, and that separates this out further. Okay, so summarizing, we have discussed that heavy flavors offer unique sensitivity to understand initial this geometry and these electromagnetic fields, and these are your take-home plots. This is for the geometry, the average V1, whereas the split V1 is basically for the electromagnetic field. And then we also discussed about this 2D decomposition of the transverse phase space, and we try to demonstrate their utility in extracting the temperature dependent. So this is of course a very general methodology, and here I just took this example to elucidate its utility, but it's of course not just restricted to heavy flavor, right? We could do this even for our standard pion, cation, proton, and so on. So here we try to elucidate that this helps us to extract the temperature dependence of this drag coefficient, for example. Okay, thank you for your attention. I'll stop here.
Thank you, Sandeep. So now question. So any question? Yes, please.
Okay, in your hydro plus EM simulation you have showed, what is the equation of state you have assumed?
The equation of state is what we get from lattice.
Okay.
Lattice, and then at below 150 or something, it is smoothly joined with the HRG.
And last question is, even if the system has very high angular momentum at the initial, just after the collision, by the angle which the system rotates is very small, right?
Sorry?
By the angle which the entire system rotates is very small. Because the time scale is very small as compared to the very large angular momentum. So instead of why we chose goes to the new basis? I mean, or the
why we chose?
Why we goes to the new basis? What is the advantage? If
New basis
that you showed, right?
No, this one, this Fourier Bessel.
Yes.
This has got nothing to do with the rotation. So it is just that we have, this is what we are measuring.
Yes.
Right? We have a 2D phase space, right?
Yes, yes.
So, and when we do the usual V2, V1, right? It is just quantifying the phi dependence, right?
Yes, that I understood.
But all I'm saying is there is also the PT dependence, which we do not quantify. We just look it by eye, right? We just leave it like this.
Okay, okay.
I mean, see, a similar plot for the phi dependence would be you just plot this n phi with phi and leave it like that. Don't extract V2 or V1. You will almost see a flat curve. You will not see any anisotropy at all.
Okay.
Right?
Thank you.
Any other question?
Sir, you show me some plot, right? F21 divided by F12 like that at last.
Sorry?
At last, can you go to the last slide? Before the thank you slide. This one. What is the CF2 and?
Right. So if you look at our new basis functions, right? This phi mn is my basis in which I am expanding this general particle distribution in the transverse phase space. When I expand, these are my coefficients, which were earlier V1, V2. If this was cosine, I mean IEIM phi, but now it is this full thing. So there are these AMN. The nomenclature is bad. Here I am calling it A, and there I am calling it F.
What will be the theta there? The theta is
where?
Theta. If you go back to this, no. If you go back to the slide, just go back.
This one?
No, sir. You define your basis functions as basal functions, right? That is a theta, right? R and theta.
Theta.
What will be the theta?
So this theta is this transverse. Maybe phi I was calling. Yeah. It's an azimuth line. Yeah.
Any other question? Okay, so maybe one question or comment. So I think you are implementing fluctuation dissipation, maybe drag, you are giving diffusion from the fluctuation dissipation and temperature. So, but in lattice and at P tends to 0, they have quite good data now with with a clear temperature dependence with a small error bar. So,
but we always try to do data driven, right?
yes, yes. But what I want to tell you earlier, okay, there was a large error bar. We had no information, but at least now some guidance is there,
Yeah.
some particular form of temperature dependence of diffusion. Of course, it's a nice way to extract, but what I want to tell, lattice already has some sort of temperature dependence.
Yeah, of course it could be. But the point is, this is an independent way of extracting.
Okay, okay, thank you.
Just one more question. While we construct a distribution of the particles by phi basis, I mean dn by d phi.
Pretty phi.
No, while we construct the phi dependency of the particle, we will consider the initial condition, right? Dn by d phi of phi is equal to dn by d phi of minus phi. That will be the initial condition. Then we will do the Fourier expansion. Then we will get the dependency, right? So what type of initial conditions you will get into, you will consider while considering these type of basis, like PT basis functions?
No, I mean, why you need it's just a distribution. So this is dn pt dpt d phi kind of thing, right? You are measuring the particles pt. So this is this guy dn pt dpt d theta, because I wrote theta there. It is this guy. So you're just measuring this.
Is there no other initial conditions?
No, this is final state phase space, particles produced.
Well, expanding it as a functions of some other basis, you are not considering any other conditions.
This you are then going to expand in that basis, right? Like earlier, what you do, you get this, but I mean, you eventually you convert it to just, you expand only the phi dependence, right? Or the theta dependence. Yeah.
Okay, then. Quickly, we have to finish before 6. Okay.
Yeah. So I have a question regarding this. So I want to understand the physical picture of what's exactly happening in the beginning of the collision. So you said that there is a deposition of angular momentum, and we have a fireball that basically tilts a bit.
Yeah.
So I've seen papers in which people treat this QGP medium that is created having rotation, sort of. So do we actually see a rotating fireball, or where does that angular momentum really go? Do we have a rotating fireball physically, I mean, really?
So what we measure are only the px, py, pz of particles, right, produced. And if you look at this, so where the angular momentum is coming from, you can just do this calculation, right? If there are two, because these are extended objects and they are separated by some impact parameter, if they are coming in this direction, then of course in the center of mass frame or in the lab frame, there is angular momentum, right? R cross P, because the R is not 0. If it is head on, then there is no angular momentum. But as soon as there is an impact parameter, there is a R cross P.
Yes, sir. Yes, I understand that part. I understand the deposition of angular momentum.
Right. Now it has to be there somehow.
Yeah. Yes.
Yeah.
So you said the PGP medium basically tilts. So the system that is created, it basically tilts, right? So we have a rotating system, sort of.
Yeah, I mean, the V1,
physical rotation.
we observe non-zero V1 is saying that the fireball is rotating in this reaction plane.
So is it like a rigid rotation? Rigid rotation of the medium?
No, there is nothing rigid here.
Like so it's expanding while rotating.
Yeah,
is that what it is?
Exactly.
Thank you.
Yeah.
Okay, then, so let's thanks the speaker once again.
Thank you.